Let's talk about what values of x make a particular power series converge. This is related to what we talked about way back in Taylor polynomials, where we saw some Taylor polynomials you kind of couldn't trust them after a certain point. They didn't seem to converge for some x values. So now we're getting toward that question of how far can I trust a Taylor series. We're doing it based on a formula that doesn't necessarily come from a Taylor series, but we're kind of bridging that gap between power series and Taylor series and series convergence here. So let's take this example. Where does this series converge? And by where we mean for what x values does this converge? You might think, oh, I've got an alternating series here, so we could think about it as an alternating series. That gets a little complicated because the alternating series test thinks about does this function decrease as n increases? Does the sequence decrease as n increases? And that depends on whether x is less than 1 or greater than 1. Like if x is 2 here, we're going to get 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. That's going to be increasing. The multiplied by n is also making it increasing. So it doesn't guarantee, we can't guarantee that this sequence is decreasing as n increases. So it depends on x. And then we could use the alternating series test to say it decreases, that when x is small enough that this sequence decreases, then we could say the alternating series test proves convergence. But then for other x's, we couldn't say that the alternating series test proves divergence. So we'd like something that's more powerful that can give us good answers for convergence and divergence. So let's try something else. So it depends on x, but it can't prove divergence. What's another thing that's a common way to test series? How about a ratio test? So for a ratio test, we usually say, what's the ratio of this term to the next term? So let's say this term and the next term. Our book defines ratio tests as only for positive things, but here we've got alternating signs. X could be negative, which could throw some negatives in there. Let's just be a little sloppy about the signs for now. We trust that it all works out eventually, especially if you think about absolute convergence. So I'll just say let's be sloppy with the signs. I'm not writing a sub n over a sub n plus 1 over a sub n, because for power series, only this first part is a sub n, but we need to do the entire stuff, including x to the n. So let's write everything here. So we'll say n plus 1, x to the n plus 1 over n times x to the n. That's our ratio for the ratio test. Let's simplify that. We got n plus 1 over n times x to the 1, or just x. And then what's the limit of that as n goes to infinity? So the limit as n goes to infinity. It's kind of hard to keep track of what's our variable here. From a sum point of view, our variable is n, and x is acting as a constant. But from the power series point of view, like a Taylor polynomial point of view, x is the variable, and n is just an index of summation. But regardless, when we're doing the ratio test, we let n go to infinity. So what's the limit as n goes to infinity over n plus 1 over n times x? Well, we're getting basically huge number plus 1 over huge number, which is basically 1. And then the x is acting like a constant when n changes. So this is 1 times x. So what does this ratio test tell us about convergence? So this ratio test says that the sum converges if the limit we get, if that limit we get is less than 1, And like I said, well, we're being sloppy with signs. It turns out you can put an absolute value here. And then the sum diverges if the absolute value of x is greater than 1, right? If the ratio test gives you something greater than 1, that means the sum diverges. And then how about if x is equal to 1 or negative 1? So what if the absolute value of x is equal to 1? That would be x equals positive 1 or negative 1. Let's skip that question for now. We'll come back to it in just a sec. So overall, we can say that the sum converges if negative 1 is less than x is less than 1. And we're not sure about equality here, so we can say we should check the endpoints separately, because that's where the ratio test doesn't give us any information on convergence or divergence. So here's the story. Math people get curious about, well, should I include negative 1? Should I include positive 1? And that's fine. I mean, pure math people, they tend to ask those sorts of questions. If I was an engineer, I would think about, well, should I really depend on the fact that this converges or diverges exactly at x equals negative 1 or exactly at x equals positive 1? You don't want to use divergent series if you think they're convergent. So that using a divergent series is kind of a bad idea if you're hoping for stable calculations. And even being close to being divergent but still technically convergent is still not a great idea. So I'd say it this way. Let's say you lived near a cliff and you wanted to put up a fence to keep your kid or dog or whatever from going over the edge of the cliff. Would you put that fence like 1 centimeter from the edge of the cliff? Or would you put that fence like a meter or 2 back to give yourself a little bit of a safety margin? I would put it a meter or 2 back, right? And so I think from an applied math or engineering point of view, we want kind of an extra safety margin. And so we're not going to worry so much about whether the equality is here or not, whether the equality is there or not, because really I shouldn't be using this sum for x right up close to that boundary of being divergent. So if you want to read more about checking the exact edges of the boundary, you can read about it in the book, and there's lots of stuff online, but I'm not going to worry about it. Two other bits of notation here. What we're deciding here is that the interval of convergence that is the set of x values where the power series converges. It might be negative 1 to 1 inclusive. It might be negative 1 inclusive to 1 exclusive. It might be negative 1 exclusive to 1 inclusive. It might be negative 1 to 1 exclusive on both ends. It would have to depend on what we found for checking the endpoints, but basically it's negative 1 to 1, and you could be careful about the endpoints if you want to. And then the radius of convergence let's think of a number line here. Here's 0, here's 1, here's negative 1. What's the radius of this interval? It's basically half the width, half the overall width, or you could say it's the distance from the center to the edge. So here the radius of convergence is 1, half the width of the interval. Some people like abbreviating radius of convergence to ROC, but ROC means something else in statistics and machine learning, so I would appreciate if we did not abbreviate radius of convergence to ROC.